Good morning or afternoon, depending if you're in second or sixth hour. I hope everybody had a great 4.5 days off. I know I for sure did. I wish I was in the class with you guys this morning, but unfortunately that is not the case. This is day one, hopefully of only 3 or 4, maybe 5 if it's worse, that I'm going to be gone. But beyond that, we got to get to the good things, and talking about good things, that's the first thing you have to do today. So please pause this recording, and one person from each row needs to tell us a good thing. And we're back. So I hope those good things were amazing, awesome, and a round of applause for those people who went. At the end of the hour, if anybody else wants to say their good thing, please do. We want to hear all the good things out of there. First off, as I said before, I'm going to be gone a couple of these days of the week. So let's go over some ground rules. Stay calm. Smile. It's going to be okay. I know some of you guys and ladies might be like, I don't, this whole video thing, him not being here is going to be aggravating. It's okay. There's no way around it. I cannot not be there. So first, if you have questions, ask your niche mates. If there's questions for me, talk to your class leaders, and they'll send me some of your concerns or the class's concerns. If at any point of this video people are getting lost, stop it, rewind it. This is going to be for you guys to watch during class, but also take it home. You guys can watch it during AC. You guys can watch it at home again. So if you get frustrated as a class, calm, move on to pause it, rewind it if we have to rewind it, so there isn't frustration. It's okay. And for those class leaders, second hour, Kaylee and Haley, if there's issues, please set them straight with everybody. And if you guys can't, email me and I'll get back to you guys as soon as possible. 6th hour, Caitlin and Kyle, take control if there's any type of issues, and contact me whenever you guys can, so I can focus on getting something better and more clear to you. So that's the biggest thing. If you have issues during this, stop the video, rewind, ask your niche mate. If the whole class has an issue, talk about it, communicate it with each other. Biggest thing that you guys are going to work on this year, especially second hour, is communication. We've got to have good communication. So let's get some bell work going here. 2 classic bell works that we've already gone over probably. What is a valence electron, and what's an electronegativity, or what is electronegativity? At the same time you guys are doing this bell work, you guys also have to get your salmon/pink handout sheet. It's got a periodic table kind of on the back with a bunch of numbers and says electronegativity scale. So please pause this so you guys can have about 2 minutes to work on your bell work. And we are back. I think this wasn't too difficult of a question or questions. It's a valence electron. We've been talking about them for, I don't know, a month. A valence electron is that outside electron who's all up for having a good time. They want to get together so they can be happy at the octet rule. They want 8 to be happy, and they're either going to give up electrons or they're going to take electrons. And those outside electrons are called valence electrons. Now, to take or to share or to give those valence electrons to another element, we have to have electronegativity. Electronegativity is just a numerical number, obviously numerical unit that says how apt or how much energy do I have to pull electrons from another element to create a bond. Some elements have a lot of this electronegativity. Some of them are very low and don't really want to form a bond. Obviously, our noble gases, they don't have any. Now, to show these electronegativities on your pink sheet, it should be similar to this. Obviously, mine is not pink all the way. These are called Pauling's electronegativity values. They range from 4 at fluorine all the way down. I believe this is going to be the smallest one, of 0.8 rubidium and potassium. And then there are no numbers on the noble gases because the noble gases have no wanting, no electronegativity value because they are happy. They're all good. So those are electronegativity values, which we'll definitely get back to a little bit later. But with these bonds, we got to talk about these bonds. And there are 2 types of bonds. We kind of went over the root of them last Friday, or whenever that day was that we were in school. Covalent / ionic. Ionic, we learned there was like charges, positives, and negatives. Covalent, we talked about co, meaning sharing. And then we also talked about valent, meaning coming from the word valence, meaning outside. So these guys share the outside electrons to form these bonds. And if we think of bonds, ionic, covalent, nonpolar, and polar covalent, that we'll talk about later, as relationships, it's going to make a lot of sense. So let's dive into here. I'm going to have both it written out for you guys on notes, but I'm also going to have visuals for you for those people who are more visual compared to auditory. Covalent bonding. Electrons are shared between 2 or more elements. It could be, now they can be similar, as in it can be oxygen with oxygen. Those are 2 elements. They could be a polyatomic, which is like a nitrate, which you guys find in fertilizer. That's going to be 4 different elements coming together. Covalent bonding, all about sharing. And we can measure them 2 different ways. There are relationships where you have covalent bonding, and it is just a euphoria. Or even a utopia, where everything's good, you know, the right electron, the left electron, they're all happy, everything's shared, it is peachy fine. Everything's split down the middle, and we call these non-polar covalent. Everything's 50-50. It's an amazing relationship. Element X and element Y happy together. They don't do anything without discussing it with each other, and they're all happy-go-lucky. Now, increasing on the not-so-even is our polar covalent. They're still sharing it. They still have those outside electrons. They're in a relationship, and it's a pretty good relationship. They're shared. They're not equal, though. They're still shared, so this is the major difference between polar covalent and ionic. It's unequal, but it's still shared. Let's say co-captains on a sports team. One does a little bit more than the other. They're still called co-captains, but one is a little bit more energetic, or the other one's a little bit lazier. Kind of a relationship before, as you guys know. In a relationship, dating somebody. Non-polar covalent, everything is just going good. Polar covalent, one person's doing a little bit more work than the other, giving a little bit more effort to the relationship. The other one's, whatever happens, happens. So those are polar covalent and non-polar covalent. Visually, let's check these out. Covalent. Let's get some highlighter going here. Not the best highlighting, but it works. So these are all shared. This is, by the way, methane. This is the gas that builds all organic compounds, which we'll talk about in organic chemistry in semester 2. But hydrogen, 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 hydrogen all share in a polar covalent way this relationship. So they're shared, not shared evenly, but they are shared. For space filling model, we have nonpolar. As you see the clouds around it, easily everything's equal. We've got a single bond chilling right here. Everything's hunky-dory, 50-50, a utopia of awesomeness. Now, up one level, polar covalent. The relationship, we're still chilling. We still have this bond between this actual contraction between them. They're actually contacting each other with these electrons. They're sharing. One is taking a little bit more leadership, but the other one's kind of like, hey, I'll give you my electron, but I'm not really, good for this. If you want it, great. If not, I'm out of here. So that is a polar covalent. Now, as you guys can see, and ladies can see here, ionic, totally different. There is a bond here, but physically, there's a gap. Right here, there's a gap. They actually don't touch each other. The larger one rips off an electron from the smaller electronegativity element, and it becomes happy because it has more electrons and it fills the octet rule. And the smaller one, it fills its octet rule too. So one becomes positive. So this guy's, wow, let's erase that. That's horrible. What kind of pen do I have here? Just give me a regular pen. There we go. So this becomes positive. This element becomes negative, and it can become 1 positive, 2 positive, 3 positive, depends on the element. But right here, there's a positive and a negative charged element. Because of the charges, that's why they stick together. And I know that's like, how do they stick together without being part of it? Think of it as a non-contact attraction. The electromagnetic field that surrounds the Earth, magnets in general, they don't have to be physically touching to have an attraction. Gravity between us and the Earth and the Moon all depends on non-contact force. It is bringing us down on Earth. The tides moving in and out. There's not like a little guy pushing the tides out and then bringing them back. It's the non-contact force of the Moon bringing the tides in and out for an ocean. So with the ionic bond, the non-contact is the positive and negative. Think of it as, once again, two magnets close together. They can be together, but they're not actually touching each other. So that's covalent. There is definitely a separation between these. Is one better than the other? No. They're just different. Just like any relationship, there's different. I'm not saying one's good, one's bad. They do have different properties, which we'll talk about later. Some are really easy at melting. Some of them don't melt at all because they have this type of bond. Let's go back to get our definition. Back. Here's a classic ionic bond. This is a lattice structure. This is sodium chloride. This is salt, what you guys and gals consumed earlier today or yesterday. At some point you were eating food, electrolytes. We have one little itty bitty way on the outside here. That electron on sodium. Sodium, remember, is in the first group. It has a charge of 1 plus, as in one valence electron. That electron gets stolen by chlorine, and it gets matched up right here. So now this has lost an electron, so it becomes positive. This has gained an electron, so it has become negative. If we do the math behind this, at the beginning, as it says, and there is still 11 positives, we lost an electron. We started with 11 electrons, but as we can see, one of them went from the sodium was grabbed by chlorine. So now we're down to 10 electrons because this one left. So doing our math, 11 positives, 10 negatives, we get a positive charge. On the other side, we start with 17 protons. We originally start with 17 electrons. This electron right here, this was added. So now instead of having 17 electrons, now we have 18. If we do math, 17 positive, 18 negative, we end up with a charge of -1 for chlorine and a charge of +1 for sodium. So this is ionic bonding. They have actual charges. They're not sharing. They actually ripped off electrons from each other. One gained one, one lost one. They're still neutral. And we know that. It's not like you eat salt and it shocks you. These are still neutral. Excuse me. Still neutral elements. Super long definition. Let's not write it all because, well, it's ridiculously long. So you can do ionic bonding. You can say electrons are donated. And then they're received. Those are the nice words for it. It's more like electrons are stolen and the other ones got robbed. That's what it is. So electrons from one element, they're the thieves. They break in, they grab your electrons, and they're out of there. And you're just left there writing a police report, and you know you'll never get your stuff back. And that's how it works. Ionic bonding creates these ions, these charges. Now the question of all questions, and I know everybody's in the crowd right now thinking the same thing as I'm thinking. How do we know which one is which? How do we know if we bind different elements together? Is it nonpolar? Is it polar covalent? Is it ionic bonding? Which one of them are they? I could give you guys a bunch of little atoms. You guys could do some crazy geometry, and you could figure it out that way. That's not going to happen. There's a very easy mathematical way to figure this out. Ladies and gentlemen, if I'm going too fast, remember, stop this so everybody can get this definition down and then proceed. So anytime if you need to stop me, please do so. But there is homework at the end. Make sure by the end of Monday you guys go forward to see what the homework is for tonight. So the math, let's get back to the math of this. We don't need calculators or cell phones to figure this out. We have to use, oh, another one. Hey, our pink sheet, I think, our pink sheet, we have to use simple math. Super simple. It is subtraction. And the biggest number we have, let's see here, which one's best? Ooh, nope. X-nay that one. But we'll just say right here. This is killing me, guys. Killing me. Here we go. This is the biggest one, fluorine. Smallest one, potassium, rubidium. We subtract them. And since we subtract them, we can have three different options. three different options we have. Three different options we have are nonpolar covalent, polar covalent, and ionic bonding. There's a really nice graph on page 176. Part of your homework is to draw this in your notes. Right now we don't need it, but if you guys and gals want a reference, it's on page 176, figure 2. Looks similar, but it's actually a better one. Better image than this. Nonpolar covalent bonds, equally sharing the utopia of relationships. It runs from, let's get runs from 0 to 0.4. If your calculations run from the numerical values of 0 to 0.4, you'll have a nonpolar covalent. If you have a number from 0.4 to 1.7, it's polar covalent. We're still sharing, but there's an unequal sharing. Here's HCl as an example. This is hydrochloric acid, which we'll use multiple times in this class. Finally, if your calculations go between 1.7 and our top of the scale, it's 3.3. If it goes 1.7 to 3.3, you're ionic bonding. Super easy math. And let's figure out where Na and Cl minus fall in. Because it says these two right here, it says that they are ionic. Let's see if the math holds up here. Let's find Na. Na is right here. It is our .9, and we're getting that with our chlorine. So let's scroll down here and do some math. We'll take the bigger number, subtract it from the smaller. 3.0 minus 0.9. And if our calculations are right, it's 2.1. Since it's 2.1, it fits in between 1.7 and 3.3. Bada boom, bada bing. Na and Cl, they are ionic bonds because they have a numeric value of 2.1. Simple math, and yes, there can be 0. If there are two elements that are the same, they would subtract, and they would subtract from each other, and they would be equal to 0. So there are 0, that's not a mistake. There can be a difference of 0. I've shared... Sorry, that was my dog, Nala. Apologize if you heard her barking. Let's do some examples then. Our examples are... fluorine and hydrogen, magnesium and iodine, oxygen and oxygen chilling by themselves together. I know that was an oxymoron. And finally, krypton plus silicon. So please pause and figure this out. Niche mates help each other. You need 1 to do the subtraction, 2 to figure out what type of bond it is, either nonpolar, polar, or ionic. You can reference your book 176, page 176, figure 2, to figure out which ones they are. So please stop this so you guys can work on it together. Hey, we're back. Fluorine, hydrogen. Fluorine is 4.0. Hydrogen is 2.1. They subtract and become 1.9. And they become ionic. and we can see our proof. Once again, here is fluorine, 4.1. Hydrogen is 2.1. Subtract those, we get ionic 1.9. Magnesium and iodine. I don't know why I'm so excited about those two, but I am. Magnesium minus iodine, so we have 2.5 for iodine. So we're working with iodine down here. Iodine's 2.5. Magnesium is 1.3. 2.5 minus 1.3 is 1.2. That's polar covalent. Oxygen and oxygen. Since they are the same, there shouldn't have been that much math involved. If you subtract the same number from itself, which are 3.5 minus 3.5, that equals 0. This is non-polar covalent. And finally, krypton and silicon. As we said before, there is no electronegativity for krypton. So, krypton is a noble gas, so it cannot form a bond, so this is impossible. So don't get frustrated if you guys didn't get an answer. It happens to be no bond. If you want to rewind this and see how we did it again, do that. If you want to talk to your niche mates to see what happened and why you didn't get those answers, please stop it so we are not lost going into anything else. If you still hear my voice, that means the class is going well and we're off to our next and last part of this lesson. In biology, we had to learn the classification: domain, kingdom, phylum, class, order, family, genus, species. We did that. Most of us can't remember that right off the top of our heads, so we had to use a mnemonic phrase. Like Dominic King Philip came over from Germany swimming. That was our mnemonic phrase. How about we remember the order? We're going to use another mnemonic phrase to talk about some unique elements. And those unique elements include oxygen and oxygen. These elements don't ever want to be by themselves. They always want to be in a compound, a mixture, even if that means having one of them match up with another one of them as an oxygen and oxygen. These are called diatomics. My mnemonic phrase for the diatomics is I bring clay for our new home. These 7 elements, iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen, these are all, when by themselves, this is going to be weird, when they're by themselves, not with any other element, they're going to find one of themselves and get together to form a bond. Iodine, there's never just one iodine chilling out in the atmosphere. There's never just one bromine chilling, or one chlorine, or one fluorine, or one oxygen, one nitrogen, or one hydrogen. They are all going to be in pairs, and that's where the word, diatomics. They've always got a buddy. Iodine's always got a buddy with iodine. Bromine's got always a partner with bromine. So these are the 7 diatomics. They're super important to know that they always are in pairs, and that's why they're called diatomics. Di meaning 2. Why is it important right now? It's not for bonding, but it's one of the things that we have to learn about bonding, as in these 7 never just are by themselves, just one oxygen or one fluorine. They're going to be bound with another oxygen or another fluorine. We just have to know this for coming up. A little bit coming up next week, this part of the week, that it's going to be important to know these. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen always form a pair when they're chilling out there in space. or in the atmosphere, or in the ground. This leads us to our homework. Part 1. Complete 1 through 5 on page 177, and then make your own mnemonic phrase from the 7 elements that are diatomics. You cannot use any of the words I use. You can't use I, or bring, or new, or home, or clay. Or for, sorry. You can't use any of the words I use. You have to make a mnemonic phrase that's school appropriate. You know what that means in our class. You can push the limit, but don't go crazy on me. Make a mnemonic phrase that makes somewhat sense, and then we'll talk about them tomorrow. So 2 parts of homework, 1 through 5, page 177, and mnemonic phrase with the letters N, F, C, L, H, O, I, and BR. 7 words, 1 sentence to make a mnemonic phrase. Have a good afternoon. For my 2 class leaders, Kaylee, Haley, if there's an issue, please contact me. Caitlin, Kyle, please send me a post or a comment so I can see and figure out if the problems we had today possibly can be corrected. Have a great afternoon. Work on these 2 homeworks, and I will also have them posted up on Google Classroom. Have a great night, and I will talk to you tomorrow.